Let's talk about the universe, not the big starry part you can see. Let's talk about the absolute bottom level of reality. The stuff that everything else is built on. If you could zoom in way past atoms, past protons and electrons, past quarks, all the way down to the smallest possible size, what would you see? Most people imagine an empty, black, still void, a perfect smoothness, a blank canvas. But that's probably wrong. At that tiniest of tiny scales, space isn't calm. It isn't empty. And it isn't still. It's a chaotic, bubbling, boiling mess, a place where reality itself is constantly fluctuating. That's quantum foam. It's a strange idea. So strange. It's hard to wrap your head around. But it comes from a very real problem in physics. The problem is that our two best theories for how the universe works don't get along. They describe reality in completely different ways, and when you try to use them together, things break. But quantum foam is what happens in that broken space. To understand it, we need to back up. We need to look at these two big ideas. One is about the very big. The other is about the very small. First, there's Albert Einstein's theory of general relativity. This is our rulebook for gravity and the universe at large scales. Stars, galaxies, black holes, the whole shape of the cosmos. Einstein's big insight was that gravity isn't a force pulling things together. It's a curve in space and time. Think of it like this. Imagine a big, flat rubber sheet stretched out tight. That's space-time. If you put a bowling ball in the middle of it, the sheet sags. It creates a dip. Now, if you roll a small marble nearby, it won't travel in a straight line. It will follow the curve made by the bowling ball. It looks like the bowling ball is pulling the marble in, but really, the marble is just following the shape of the space it's moving through. That's general relativity in a nutshell. Mass tells space-time how to curve, and the curve of space-time tells mass how to move. It's a beautiful, elegant theory, and one of its key features is that space-time is smooth. It's a continuous, geometric fabric. It can bend and warp, but it doesn't have gaps or jitters. It's like a perfect, polished surface. This theory works incredibly well for describing planets orbiting a sun or light bending around a galaxy. It's been tested again and again, and it holds up. Then we have the other side of physics, quantum mechanics. This is our rulebook for the very small, the world of atoms, electrons, and all the other tiny particles that make up everything. And this world is nothing like the smooth, predictable world of general relativity. It's a world of probabilities, uncertainties, and weirdness. In the quantum world, things don't have a definite location until you measure them. A particle can be in many places at once, existing as a wave of probability. Everything is fuzzy. The most important rule for our discussion is the Heisenberg uncertainty principle. The uncertainty principle says you can't know certain pairs of things about a particle at the same time with perfect accuracy. For example, you can't know exactly where a particle is and exactly where it's going. The more you pin down its position, the more uncertain its momentum becomes, and vice versa. It's a fundamental limit on what we can know about the universe. But there's another version of this principle. It doesn't just apply to position and momentum. It also applies to energy and time. You can't know the exact amount of energy in a system for a specific tiny sliver of time. This means that for very, very short moments, the amount of energy in a patch of space can fluctuate wildly. It can basically borrow energy from nothing as long as it pays it back almost instantly. This isn't just a theory. We see the effects of this all the time in particle accelerators. The vacuum of space, which we think of as empty, is actually fizzing with these energy fluctuations. These fluctuations can momentarily create pairs of particles and antiparticles, which then annihilate each other and disappear. We call these virtual particles. They pop into existence from nothing and vanish back into nothing in a flash. The empty vacuum isn't empty at all. It's a busy, active place. So now we have our two theories. General relativity says space-time is a smooth, calm, geometric sheet. Quantum mechanics says that on small scales, everything is uncertain and fizzing with random energy fluctuations. What happens when you try to put them together? What happens when you try to apply the rules of quantum mechanics to the smooth fabric of space-time itself? That's where the trouble starts, and that's where quantum foam is born. Let's go back to our rubber sheet. General relativity says it's smooth, but quantum mechanics says that if you look at a very, very tiny patch of that sheet for a very, very short amount of time, its energy has to be uncertain. It has to fluctuate, and what does energy do in general relativity? It curves space-time. Remember, mass is a form of energy. So if the energy in a tiny patch of space is fluctuating like crazy, then the curvature of space-time in that patch must also be fluctuating like crazy. The smooth, gentle rubber sheet is gone. When you zoom all the way in, it becomes a chaotic, violent, bubbling mess. The curvature of space is no longer a simple dip from a bowling ball. It's a seething landscape of tiny hills, valleys, and tunnels that are constantly appearing, twisting, and disappearing. The geometry of reality itself becomes fuzzy and probabilistic. This chaotic, roiling state of space-time at the smallest possible scale is what the physicist John Wheeler called quantum foam. He came up with the term back in the 1950s, and it's a perfect metaphor. Think of the surface of the ocean. From a high-flying airplane, it looks perfectly flat and smooth. But if you get down to the surface in a small boat, you see it's a mess of waves, crests, and troughs. If you look even closer, with a microscope, you'd see tiny bubbles and foam. The smoothness was just an illusion of scale. Wheeler proposed that the same is true for spacetime. So what is this scale we are talking about? It's called the Planck scale. The Planck length is about 1.6 times 10 raised to the power of 35 meters. That number is so small, it's almost meaningless to us. To give you a sense of it, if you were to scale up an atom to be the size of the entire observable universe, the Planck length would be about the height of a tree. It is the fundamental pixel size of reality. At this scale, our normal understanding of space and distance breaks down. The idea of a smooth line between 2 points doesn't make sense anymore. The path is so twisted and distorted by the foam that the very concept of distance becomes fuzzy. The same goes for time. The smallest possible unit of time is the Planck time, which is the time it takes for light to travel 1 Planck length. Below that, time itself dissolves into the foamy chaos. So what is this foam made of? It's not made of anything, really. It is space-time. It's the inherent nature of space-time when quantum mechanics is taken into account. The bubbles in the foam are these intense microscopic fluctuations in the curvature of space. They are like tiny, short-lived gravitational fields. Wheeler speculated that these bubbles could be incredibly exotic. Some might be tiny, virtual black holes winking in and out of existence. Others could be microscopic wormholes, tiny tunnels connecting one part of space to another, or even connecting our universe to others. Imagine a landscape where tiny bridges to everywhere and everywhen are constantly forming and collapsing in a fraction of a second. That's the wild world of the quantum foam. This isn't just a weird thought experiment. If it's real, it has profound implications for our understanding of the universe. For one, it could change our understanding of the vacuum. The vacuum of space has energy. We call it vacuum energy or dark energy. It's the stuff that's causing the expansion of the universe to accelerate. Physicists have tried to calculate how much energy the vacuum should have based on all the quantum fluctuations we know about. The problem is, the number they get is absurdly large. It's 120 orders of magnitude larger than what we actually observe. This is famously called the worst prediction in the history of physics. Quantum foam might offer a way out. The calculations we do assume a smooth background spacetime, but if spacetime itself is a churning foam, the very nature of those energy fluctuations could be different. The foam might act in a way that naturally cancels out most of that enormous energy, leaving just a small amount we see today. We don't know how this would work, but it's a possibility. It could also change our understanding of the beginning of the universe. Where did the Big Bang come from? The standard model says it came from a singularity, a point of infinite density, where the laws of physics break down. But maybe that's not the whole story. Maybe the universe we see is just one bubble in an eternal quantum foam that got big. Perhaps the foam is the true, timeless state of reality, and universes like ours are just fluctuations that happen to inflate and last for a while. Our entire cosmos could have started as a random bubble in a much larger, pre-existing foamy reality. There's another interesting idea. Does the foam affect things that travel through it? Some physicists think so. Think about light traveling through water versus traveling through air. It moves at different speeds. The idea is that space-time isn't perfectly empty. It has a texture, a graininess, because of the foam. This could mean that not all light travels at the exact same speed. Specifically, high-energy photons of light like gamma rays might interact with the tiny bubbles in the foam more than low-energy photons like radio waves. This interaction could slow them down. Just a tiny, tiny bit. You would never notice this over short distances. The effect would be minuscule, but over billions of light years it might add up. Imagine a huge cosmic explosion like a gamma ray burst happening on the other side of the universe. It releases photons of all different energies at the exact same moment. If those photons travel for billions of years to reach our telescopes, and if the high-energy ones are slowed down by the quantum foam, they should arrive a split second later than the low-energy ones. This is a testable prediction. We have telescopes, like the Fermi Gamma Ray Space Telescope, that can detect these bursts with incredible precision. Scientists have looked for this time delay. So far, they haven't found it. Light from distant bursts seems to arrive all at once, regardless of its energy. What does that mean? It doesn't necessarily mean quantum foam isn't real, it might just mean that this particular effect doesn't happen, or that it's even smaller than we thought. It puts limits on what kind of foam is possible. It rules out some of the more dramatic models, but the basic idea remains. So if we can't really see it directly, why do physicists take this idea so seriously? It's because quantum foam isn't just a wild guess, it's a logical consequence of combining our two best theories. If both general relativity and quantum mechanics are correct, then something like quantum foam must exist at the Planck scale. The fact that we can't handle it mathematically is a sign that our theories are incomplete. We are missing something big. This is the central quest of modern theoretical physics, to find a single theory that can unite gravity and the quantum world. A theory of everything. The two main contenders for this are string theory and loop quantum gravity. And both of them have their own version of quantum foam. In string theory, the fundamental building blocks of reality aren't particles. They are tiny, vibrating strings of energy. What we see as a particle, like an electron, is just a string vibrating in a particular way. In this view, space-time itself is made of these strings. The quantum foam would be the chaotic, energetic dance of these strings at the Planck scale. Loop quantum gravity takes a different approach. It suggests that space-time isn't continuous at all. It's made of discrete, indivisible chunks. It's a network of interconnected loops. Think of it like a piece of fabric. From a distance, it looks smooth. But up close, you see it's made of individual threads woven together. Loop quantum gravity says space-time is like that. The quantum foam in this picture is the constant reweaving of these fundamental loops. It's a dynamic network called a spin foam. Both of these theories are attempts to describe the foamy nature of reality at the bottom. They are mathematically incredibly complex, and neither one has been proven. But they both agree on the basic premise: the smooth, simple spacetime we see is an illusion. The underlying reality is something much stranger and more complex. So how can we get a better grip on this? How can we ever hope to prove that the foam is real? The direct approach is probably impossible. Building a machine that could probe the Planck length is so far beyond our technological abilities that it's basically science fiction. It would require an accelerator the size of our galaxy, so we have to be clever. We have to look for indirect evidence. The search for tiny delays in gamma ray arrival times is one such method. Another is to look for clues in the very early universe. The cosmic microwave background, or CMB, is the leftover heat from the Big Bang. It's a faint glow of light that fills the entire sky, and it's not perfectly uniform. There are tiny microscopic variations in its temperature. These tiny ripples in the CMB are believed to be the ghosts of quantum fluctuations from the first fraction of a second of the universe's existence. In that moment, the universe was incredibly small and dense. Quantum effects were dominant. The fluctuations we see in the quantum foam today would have been happening then. Then a period of rapid expansion called inflation is thought to have stretched the universe enormously. It would have taken those microscopic quantum jitters and blown them up to astronomical sizes. These are the ripples we see in the CMB today. So when we look at a map of the CMB, we might be looking at a fossilized, magnified image of the quantum foam from the dawn of time. This is probably the closest we've come to seeing evidence for this kind of quantum fuzziness at the foundation of reality. Another path could come from gravity itself. Gravitational waves are ripples in the fabric of space-time, created by massive events like two black holes colliding. Our current detectors, like LIGO, can only detect the most violent, large-scale waves. But as our technology improves, we might be able to build detectors so sensitive that they could pick up on a background hiss of gravitational waves. What would cause such a hiss? It could be the quantum foam itself. The constant bubbling and whirling of space-time at the Planck scale might create a faint, constant background of high-frequency gravitational waves. If we could ever build a detector sensitive enough to filter out all the other noise and hear this gravitational wave hum from the foam, it would be direct evidence of this fundamental chaos. It's a strange thought to sit with. The ground beneath your feet, the chair you're sitting on, the very air you breathe, all of it rests on a foundation of pure chaos. A reality that is constantly tearing and reforming at a scale so small, we can never see it. It makes you wonder if some of the universe's biggest mysteries are connected to it. Take dark matter, for example. We know there is some invisible substance whose gravity holds galaxies together. We don't know what it is. Could it be related to quantum foam? Some very speculative ideas suggest that the foam might interact with ordinary matter in a way that creates an effect that we perceive as the gravity of dark matter, or that certain long-lived fluctuations in the foam could themselves be particles of dark matter. These are long shots, but in the absence of evidence, physicists explore every possibility. And what about information? There's a famous problem in physics called the black hole information paradox. According to quantum mechanics, information can never be destroyed. But according to general relativity, if you throw something into a black hole, the information about it is lost forever, trapped behind the event horizon. When the black hole eventually evaporates through a process called Hawking radiation, that information seems to be gone for good. This is a major conflict. Stephen Hawking, who first proposed this problem, later changed his mind. He suggested that maybe information isn't lost. Maybe it gets scrambled and stored on the event horizon, and then slowly leaks back out. The quantum foam might play a role here. The chaotic nature of space-time at the event horizon of a black hole could be the mechanism by which information is encoded and eventually returned to the universe. The violent bubbling of the foam could be the key to solving this deep paradox. In the end, quantum foam represents the edge of our knowledge. It is the place where our most successful theories fail, and therefore it's the most fertile ground for new discoveries. It forces us to question our most basic assumptions about reality. What are space and time? Are they fundamental, or are they emergent properties of something deeper? The foam suggests they are emergent. Just as the wetness of water is an emergent property of trillions of H2O molecules, perhaps space-time, as we know it, is an emergent property of a chaotic, information-based network at the Planck scale. Thinking about it can feel a bit unsettling. The solid, stable world we experience is just a large-scale average. An illusion of calm painted over an infinitely deep and turbulent ocean of quantum uncertainty. Every cubic centimeter of space around you right now is seething with this unimaginable activity. Tiny wormholes, virtual particles, and fluctuating geometries are popping in and out of existence faster than thought. But it's also a deeply humbling and beautiful idea. It shows us that the universe is far more intricate and mysterious than we can possibly imagine. We live on the smooth surface, but the real action, the fundamental engine of reality, is happening in the foam below. It's a reminder that we are just beginning to scratch the surface of understanding what this universe is. The smooth space of Einstein and the buzzing world of quantum mechanics are two sides of the same coin. Quantum foam is the mysterious pattern on the edge of that coin, and we are still trying to figure out how to read it. It is the texture of reality itself.